Hickson from Google Research, and I'm presenting Sharing Decoders, Network Fission for Multitask Pixel Prediction, where we explore predicting three tasks: surface normals, depth, and indoor semantic labels with the shared decoder. First, some prior work. Here we will discuss two current camps of multitask learning. The first is soft parameter sharing. This is where we take several independently trained networks and try to regularize the parameters between them to predict several tasks. An example of this is cross-dish networks and sluice networks. However, in practice, these types of networks have issues as even more parameters need to be learned, making networks very large and complex. The second is hard parameter sharing. Hard parameter sharing is when we have a fixed shared feature space and a fixed independent feature space that we are trying to learn. However, little exploration has been done on where to separate hard parameter sharing for multitask encoder-decoders. This is what we aim to fix. Encoder-decoder architectures have become a popular method of pixelized prediction tasks. An example of this is AdaptNet++. The question is, how can we best modify these to do multitask pixel prediction? Current popular hard parameter sharing methods can be seen as parallel to the early fusion methodologies for different inputs, where two inputs were combined at the beginning of the network and then fed into an encoder. Here we have the inverse. We have a shared encoder, which we split at the earliest point, and then we have a decoder for each separate task. This is the standard method that many people use today. We call this early fission. The next point we could split at is one after the decoder block being shared. This is the first middle point. We call this early mid-fission. This includes any blocks between the first and the last. Next is the next middle block to be shared, with only a final decoder block being task independent. We call this mid-fission. Note, this would be the same if you had several blocks more in this decoder as well. Lastly, we have the last potential split, late fission, where all decoder blocks are shared and the output is simply split for each task class. This is one encoder-decoder that is predicting many tasks with all layers shared. Here we examine each one of these possible fissions in an ablation study with two tasks, surface normal and some estimation and semantic labeling on the CNET dataset. To test each method, we train from scratch and compare with initializing on a network trained on surface normals and initializing on a network trained on semantic labels. Note that the early mid and mid fission outperform when initialized with normals. We show here also the percent improvement over the single task model, the number of floating point operations, which we call flops, and the percent improvement per flop increase percentage, which we call pip-fip. This can be used to explain the percent improvement compared to how much larger the network gets. We use this metric as it's easy to make a network substantially larger and get improvement, and this keeps the concept of improvement with similar capacity. Note that our proposed mid-fission method takes the fewest parameters, only requiring 0.017% more flops than the single task label method. We also do a variability ablation study showing that this is reproducible over several runs, even with different random training. Here we show results on all three modalities. Note that mid-fission is the only method to have a positive percent improvement and positive improvement per flop increase percentage. Our method improves on all three tasks. Next, we show our method compared to some of the state-of-the-art methods on the NYU V2 dataset, both the 13 and 40 class split. Note that these are all previous results are using large early fission, 1.5 times single task size, or soft parameter sharing networks, more than 2 times single task network size, versus ours, which is only 0.017% more flops. But yet we are still outperforming. And here we show our results on ScanNet V2. Note that they are well surpassing state-of-the-art results with the larger server network on the left, and we also have our mobile results on the right that run at greater than 30 FPS on a Pixel 3 mobile phone. And here are some of our qualitative results. From left to right, you have RGB, ground truth surface normals, predicted surface normals, ground truth labels, and predicted labels. We also show a real-time recorded demo quantized via GIF of the multitask model running on a mobile phone. And finally, we show some real-time AR effects that can be done with this type of network. These were all created with the real-time model we presented here using a combination of surface normals, depth, and indoor semantic labels. Having all three of these modalities allows the floor to be mapped more accurately in all of these. Thanks. See our paper for more questions.